believe it or not, there are two ways to solve this limit. I personally prefer the second way, so stick around, or obviously you can skip ahead to see both solutions, and obviously try them for yourself first. So the first solution is found by using L'Hopital's rule. So we take the limit as x approaches 0, and for L'Hopital's rule, we take the derivative of both the numerator and denominator. So the derivative of the denominator is simply 1, and the derivative of the numerator, so derivative of 1 is 0, so we don't write that down. And now we have this term here, and this term can be split up like this, and we can do the product rule. So we have this term, negative e to the 3x, and we have cos of x squared. So we take the derivative first of negative e to the 3x. So derivative of e is always going to be e, so we're going to keep e to the 3x, and then we do the derivative of 3x, which is 3, and we keep that negative, and it gets times by cos of x squared, which remains the same. And let's extend this line, and now we're going to add minus e to the 3x, so we can take away this positive, because we keep this now the same, we take the derivative of this. So first off, the derivative of cos of x squared is going to be sine of x squared, but the negative, so we're going to change that negative into a positive, and then do the derivative of what's inside. So that's going to be 2x times by 2x. And now we've done L'Hopital's rule as far as we can, and now we can actually evaluate this limit. So if we substitute in x equal to 0 over here, e to the 3x becomes e to the 0, and anything to the power of 0 is 1. So we have minus 3 times by 1, and cos of x squared, when x is 0, is cos of 0, and cos of 0 is 1 again, so times by 1. And now we have to substitute in 0 here, and I'm not going to bother really to even think about these, because I've already seen this x here. So I'm going to substitute in 0 there, and it's going to make this whole thing 0 immediately. So plus 0. So what we're left with is just negative 3. And that's the first way to find the solution. And now I'm going to find the solution to be negative 3 in another way. And I've said that I preferred this way. And it's actually using Maclaurin polynomials. So these are polynomials that I've just memorized, and obviously I can derive them, and maybe I'll save that for another video, the derivation of Taylor and Maclaurin polynomials. But here are they in their already derived form. And so, as you can see, what I'm going to try and do is substitute in this and this into this formula. But now, obviously, there's a problem, because this is an x and that's a 3x, and that's just an x, and that's an x squared. So I'm going to change these slightly to suit me. So first of all, we find the Maclaurin polynomial of e to the 3x. So e to the 3x is going to be 1 plus, and now what I'm essentially doing is replacing every time I see an x with 3x. So here's an x, and I'm going to replace that with 3x over 1 factorial, which is just 1, plus, and now the x squared, so it's going to be 3x squared over 2 factorial, which is just 2. I'm not going to bother with any more terms. And so now I'm going to do the same for cos of x, but obviously now substituting an x squared wherever I see an x. So cos of x squared is going to be 1 minus x squared squared, which is simply x raised to the 4th power over 2 factorial, which again is just 2, plus x squared to the 4th power, which is simply x to the power of 8 over 4 factorial, and then subtract, and we won't bother about the rest of the terms either. So now we have this useful bit of information, and as you can see here, they actually multiply together in the same term. So I'm going to multiply these together and get a few terms out so that it's easy to work with. So now e to the 3x times by cos of x squared is going to be, so I multiply these ones out. It's basically like a FOIL method where you distribute. So I can distribute this 1 there, and I can continue distributing. I'm not going to do all of them because I won't end up needing powers that are so high, but I will do a few just to demonstrate. So 1 times 1 will be 1, and then 1 times by negative x to the 4 over 2, it's going to be negative x to the 4 over 2, and then I'm not really going to do that because x to the 8 is going to be huge. It's going to have the degree of x is very large, so I'm not even going to bother. But I will distribute this one this way now. So we have plus 3x, and I'll distribute that one there, plus 9x squared. As you can see, I've just taking the square in over 2. And then, as I said, like we can multiply all these different ones that I haven't shown you. But it's really not necessary for this particular purpose. So now we carry on, and since we have this in a Maclaurin polynomial form here, we'll carry on with our limit and see what we can work with. So this is our limit here, and we have the limit as x approaches 0 of 1 minus e to the 3x times by cos of x squared. But now we're going to substitute in that because it's equal. 1 minus x to the 4 over 2 plus 3x plus 9 over 2 x squared plus dot 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 all over x. So now you'll notice that those ones cancel and we get this negative will distribute, and so the negative times by that will become x to the 4 over 2, positive x to the 4 over 2, minus 3x, minus 9 over 2 x squared, all over x, and then still again, plus all these terms that are arbitrary, and you'll see why, and you'll see now why they are so arbitrary. So now we can actually take this x out of the numerator as a common factor and then cancel it. So I'll go ahead and do that. So we have the limit as x approaches 0, and I take an x out, so we have x cubed over 2 minus 3 minus 9 over 2x plus dot dot dot. Oopsie. All over x, and those x's cancel. Now we can actually evaluate this limit. So we substitute an x equal to 0, and that becomes 0, that term becomes 0, and all these other terms are also going to become 0. And that's essentially why we ignored all of the terms with higher degrees of x, because we were going to be dividing by an x through all of here. And so if we have if we have terms of degree where x is raised to a high degree, when we're going to divide by x to the first degree, we're still going to have a high degree of x. So substituting an x equal to 0 will just yield 0. So it's kind of arbitrary. We know that it's going to get cancelled out. So as you can see here, like what happened with the x cubed over 2 and the negative 9 over 2x, when we substitute in x equal to 0, those disappear, and we're simply left with the answer, negative 3. So although this is a longer solution than the L'Hopital's rule one, I still prefer it because I think it brings together like different sectors of maths, and it makes it more interesting to delve into, and it's a more satisfying solution, I find. Anyway, you can let me know which solution you prefer, and I hope that you managed to do both ways by yourself before I went through the solutions, and otherwise, I hope you learned something. And if you like this video, please do leave it a like and consider subscribing. I've got 94 days ahead of me, so there's a guarantee that I'll be releasing content. Anyways, thank you.